Hey, today's little gem is something called Rolle's theorem. And here's what it says. It says that suppose that a function f is continuous on a closed interval a, b, differentiable on the open interval from a to b, and that f of a equals f of b, meaning it has the same value at the two endpoints. Then Rolle's theorem says that there exists some point c in the interval from a to b such that the derivative at c is equal to 0. And before we sketch out a proof, let's look at a quick picture. Here's a function f. It's continuous on the closed interval from a to b. It's certainly differentiable on the open interval from a to b. And I've tried to draw it so that f of a is equal to f of b. Well, there is some point in between a and b where a tangent line to the curve is horizontal, so the derivative at that point is 0. And that would be the point C that Rolle's theorem guarantees has to exist. Turns out this is a critical point of the function f. Okay, let's sketch the proof. The proof breaks down into 3 cases. And the first is kind of the silly case. If f is a constant function, if it has the same value everywhere, then its derivative is 0 everywhere on the interval from a to b. And so we pick any point between a and b, and the derivative there is 0. The second case is the most interesting case because the third case is very similar to the second case. And if f is not constant, then somewhere between a and b, there's some point where the function has a value either larger than the value at the endpoints or smaller than the value at the endpoints. And so in this second case, we'll consider the situation where there's some point in a between a and b where the function value at that point is larger than the function value at a, which is of course the same as the function value at b. Well, f is a continuous function on the closed interval from a to b, so by the extreme value theorem, f has to attain an absolute maximum on the closed interval from a to b. And it can't possibly be at a or b because we know there's this value x where the function is larger than it is at a and b. And if the absolute maximum doesn't occur at one of the endpoints, then we know it has to occur at a critical point. Call that point c. And since c is a critical point, that means that either the function is not differentiable there, which is not the case because the function is differentiable on all of the interval from a to b. And that means that the other possibility has to be the case that the derivative at c is equal to 0, which is what we were looking to show. And then finally, there's the third case. It doesn't necessarily have to be true that there's some x in the interval from a to b where f of x is greater than f of a. But if that's not the case and the function is inconstant, then that means there is some x in the interval from a to b such that the function value at x is less than the function value at a and at b. Well, in that case, we make the same argument that we made for case 2, except that we use an absolute minimum instead of an absolute maximum. And there has to be an absolute minimum. It can't occur at the endpoints, and so it must occur at a critical point, and at that critical point, the derivative is 0. And so that completes our proof of Rolle's theorem. Rolle's theorem. Its main purpose for existence is to prove something called the mean value theorem, which we'll be studying shortly. It's very rarely used directly and on its own, but we can look at one kind of cute application of Rolle's theorem before we call it a day. Let's see if we can use Rolle's theorem to prove that the polynomial function f of x equals x cubed plus 3x minus 1 has exactly one real root, or real 0. We start by observing that f of 0 is equal to negative 1 and f of 1 is equal to positive 3. And that tells us that there's some point that I'm calling a between 0 and 1 such that f of a is equal to 0 by the intermediate value theorem. This function is a continuous function because it's a polynomial, and if it's negative at 0 and positive at 1, then somewhere between 0 and 1 it has to cross every value between negative 1 and 3, including the value 0. And so that tells us that this function has at least one real root. We know even more. It has at least one real root between 0 and 1. Now we have to show that it doesn't have more than one real root. All right, suppose that's not the case. Suppose that f of b is equal to 0 for some value of b different from a. Well, then we have f of a equals f of b. F is a continuous function over all the real numbers, so certainly on the closed interval from a to b or b to a, depending on which one is smaller. It's differentiable from a to b or b to a again. And so Rolle's theorem tells us that there's some point c between a and b where the derivative is equal to 0. But the derivative is 3x squared plus 3. And 3x squared plus 3 is not equal to 0 for any real numbers. There's lots of ways to see that. You can try to solve that equation for x. You'll find that you get a complex answer. Or you can just think of it as, well, x squared is positive, so 3 times x squared is positive, and you add positive 3, you're going to get a positive number there, never 0. And that means that it's not possible that there was this b, this other point b, where the function was equal to 0. There's only one real root of this function. That was Rolle's theorem. There is no homework on it. As I mentioned, we will basically be using it to prove the mean value theorem coming up sometime very soon to a calculus class near you. See you soon. Bye.